So I'm Bill Snow. I'm from ON.Lab. ON.Lab's a nonprofit. We're going to talk about ONOS today. ONOS is not the only thing that we work in. We also have a cloud operating system. We have a virtualization platform. And we have Mininet, which is a network emulator used in many universities, many online courses, and in actually many corporations to help with testing and emulating SDN. Okay, so let's talk about ONOS. Okay, so this is what we'll talk about today. I want to help you learn more about ONOS, what the requirements were that we set out to meet, what design points we looked at, what capabilities it has. And there's a question I think that is really important. It's can open source really meet service provider demands, right, for availability, for scale, for performance? And of course the answer in my mind is yes. We're also going to talk about service provider transformation. I'll talk about the types of POCs and deployments that we're going through and which are on our horizon. And an important question behind that one is transformation only for greenfield? And again, my feeling is definitely not. Not based on what I see and what we're doing. And then we'll also give you information about the community and the traction that ONOS is getting. Okay? And by the end of the talk, I hope you'll have these key points. ONOS has been purpose-built right from the beginning for operators. We're gaining a lot of momentum, as shown by the POCs, the deployments, the performance we've achieved, and the community growth. So let's dive in. Okay, so this is what's happening out there. You all know it. To sort of set some context, we're moving from boxes that are vertically integrated to disaggregation, where you have applications moving to commodity servers, you have control planes moving to a network operating system, and you have hardware moving into white box environments. And this is an important evolution because that separation allows each of those layers to evolve at their own natural rate and not be as dependent upon each other. And the other point I'll make is I think it's important to make the distinction of an operating system. An operating system manages a number of resources on behalf of its users or its applications. And in doing so, it's very important that you focus on what types of abstractions can you provide for those applications to make life easier. And the abstractions, that's been a major focus of ours since the beginning. Okay, why is this good for open source? And we heard a lot of this yesterday, right? And the main reason is where the value is, right? Vendors can derive a lot of value in applications, in orchestration. They can derive a lot of value out of innovations at hardware or the agents that run in the hardware. And they derive a lot of value from the integrated solutions that they provide. It's a little bit harder to provide value at the control plane. This is an expensive thing to develop. And it also has requirements for interoperability across vendors. So that requirement for interoperability and the opportunity to amortize all these expenses across a number of vendors makes something like the control plane a perfect candidate for open source. Talk a little bit about the journey we've been on with ONOS. ON.Lab started 3 years ago, and ONOS started almost immediately after we got started. We went through 3 prototypes because we were trying very hard to prove to ourselves that we could actually build a system to handle the types of requirements that we were after. And it's a seriously difficult engineering challenge. And so we worked really closely with distributed systems people from Google, from Microsoft, all the experts that we could find. We went through 3 iterations, trying different designs, using different types of open source, using different types of database to see what would work. And we got to the point where we really believed in what we were doing from an architecture perspective, and we came open source with the Avoset release in December. That was all about the architectural integrity. It had a very powerful user interface because we think you should be able to easily see your network and be able to zoom in, zoom out, and focus on different parts of it. We put a lot of effort into helping the community get on board by wiki, through tutorials, through videos. But what we didn't worry about at that point was performance, right? Because if you optimize too early, then you screw things up. Okay, so we were all about correctness in architecture, and then after we came out in December, we focused on performance. And so the Blackbird release came out in early March. That was all about how do we get the performance with the architecture we have and keep scale. And we are easily able to handle over 1 million flow operations per second and much lower than 100 milliseconds to react to network events, all while keeping high availability. Okay, and I'll show you a lot more on the performance later in the talk. Okay, we're at the Cardinal release right now. That's coming out at the end of this month. And the theme of Cardinal has been all about enabling POCs and service provider use cases. And I'm going to go into a lot of detail on some of these later in the talk, but there's interesting work around the central office, how you do fabric control, how you help transition that central office to be architected more like a data center. We've also put an emphasis on the use cases that show migration. Okay, how do you take your existing network and start putting SDN into it? Okay, we'll have another release in August and another one in December. We're on 3-month release cycles. Towards the end of the year, we'll continue accelerating the number of POCs that we're doing, more lab trials, more deployments, all with the intention of going into production in early 2016. Talk about the requirements. Okay, it's a busy slide, lots of numbers on it. The point of this slide is these are big networks, right? They're from the core to the edge. There's a huge number of elements and ports, right? And so any operating system has to be able to handle a large network like this. So let's talk about what the key architectural challenge is given those types of requirements. And the first abstraction that we set out to provide was a global network view, which is what that little diamond of the tail is on here. And so an application is able to see the entire network and act on that, right? So you could program it as a graph, for example. Okay, and if you're going to provide that global network view across a large network like that, the first thing that you're going to find is you have a huge amount of state, right? And the amount of state is on the order of half a terabyte to a terabyte. So lots of state. Second thing is that we anticipate running a lot of demanding applications, and those applications are going to require a lot of throughput in the requests that they make of the network. Okay, and you're looking at on the order of asking for 1 million path setups per second, and every path setup results in multiple operations to set up flows in your devices. And so on the order of 6 million network state operations per second. And you have to be really reactive to the network. You definitely have to be less than 100 milliseconds, and ideally, you want to be less than 50 milliseconds. And reactive meaning noticing that something happens, bringing it up to the application, letting the application make whatever changes it wants to, those changes propagating down to where you've reprogrammed the data plane. Okay, high throughput, low latency, consistency, and high availability. Okay, this is a really hard engineering challenge. So the approach we took was to build a distributed system, and it uses a scale-out design, learning the things that we've learned from building large web environments and data centers. Each instance is identical. You can easily add and remove instances as you need to. As instances fail, it's no problem. The others take over for it. Each instance is a master for a subset of the network. And the beautiful thing from an application viewpoint or from a device viewpoint is that ONOS looks like a single system. Okay, going a little deeper into the architecture tiers. Okay, the applications first interact with our northbound interfaces. And very important abstractions here. I mentioned the one for the global network view, but there's a couple of others that are equally important. The first is the intent framework. And from the beginning, we've had an intent framework so that an application can tell the network what it wants, okay, what it needs, and it doesn't have to worry about telling it how to do it. Right? So we're really trying to simplify how an application interacts with the network operating system. Another one is flow objectives. This is a fairly new one. And this has to do with the fact that switches have different table structures. And you do not want applications and the operating system to have to know a lot about what the exact table structures are in these different devices. So a flow objective lets you indicate what type of processing you'd like to get out of that flow, and then goes down through the operating system to set that up for you, whether it's a Corsa hardware device or some other vendors. Distributed core is the most important piece because it's here that you get your scale, you get your availability, your performance, and your persistence. And I'm going to talk a lot more about the core. Southbound is where you discover your network, you observe, you react to problems, you program the network, and you configure it. And probably more important is it insulates the rest of your operating system and your applications from the intricacies of the devices and protocols. It's modular. You can put in whatever protocol you want to support. Today we have OpenFlow, NetConf. We're going to be demonstrating some TL1 at ONS, and there's some others in progress as well. Okay, this is an eye chart, but the point of this slide is the software is extremely modular, and we've put a big effort into having it be well architected, faceted, so that one, it's easy for us to develop, two, it's easy for us to test and maintain, but even more important is it's easy for people who take this source code to adapt parts of it, add pieces to it, swap pieces out. So as a vendor that wants to add value in a particular way, it's actually pretty easy to do so. Okay, so we're going to dive into some detail on control plane state, because this is one of the areas that it's maybe not so obvious, but it makes a huge difference in what your operating system is able to do. And there's a lot of different state, like the switch to controller mappings, the topology, the intents, and so forth. And the questions that you want to ask as you're building this system is, how is this state produced? How is it consumed? Does it have durability requirements? Meaning, if something fails, can you go somewhere and get a copy of it? Or do you have to rebuild everything? And is it consistent? Right? Is it the same from instance to instance? So I'm going to look at a couple of them in more detail. Let's start with topology. This is your observed network state. The truth is in your data plane. The best solution to handle this state would be something that is very fast to track change, something that is very low cost from an application perspective to get access to, and something which scales well with your network growth. So it's fast in this implementation because it's eventually consistent. If you tried to be consistent with all instances, you'd have to pay a big price for all the handshakes. Okay? So we go with eventually consistent for topology. Low cost to the application. We put the full topology in memory on each instance. So it's fully replicated across every instance, and all an application needs to do is get it right out of memory. It scales well because it's sharded. Each instance is responsible for a portion of the network. And because it's eventually consistent, each one of those does have to eventually get to the exact same view of the network state, and that's handled through something called Gossip, which uses a technology called vector clocks. So that's topology. Let's look at a different one. Flows. Flows control your data plane forwarding rules. Unlike the topology, the control plane is a source of truth here. And the best solution for flows is something that's partitioned naturally, something that really takes advantage of the fact that you have localized read-write access to the device. And it has to be strongly consistent, because you can't have the control plane thinking that the flow state is different than what's actually on a switch. Okay, so it's naturally partitioned by the forwarding element, so that's good. You get very fast local read-write. And we make sure it's strongly consistent to one node. Okay, so we back up the flow table from one instance to another instance. And we do a very important optimization on this, is that we take that backup to the instance that will become the master in a failover. Because when you do a failover, you do not want to have to rebuild the flow table. Okay, so that's two different types of state. I won't go through any more. You can kind of get it. Each state has its own particular differences. And I think an important question that I get a lot is, why not use a single logically centralized store? Why not use a Cassandra, a Mongo, or some other of these NoSQL databases? And we've been there. And it was great for prototyping, but you'll never get to where you need to get to with them. And they tend to be tuned for either high availability or strong consistency. And typically they fail to exploit the access patterns and the locality constraints that you have of some state. So if you really care about getting HA, scale, and performance, and providing abstractions, because abstractions cost you some amount of code, and having security, because that also costs you some code, then you really have to go to a very detailed level of understanding the appropriate store for the type of state. Okay, performance is a big deal for us. So what is our performance? And honestly, the industry hasn't done very well on performance and control plane state. I mean, Cbench is all about I/O loop of your OpenFlow implementation, right? Very minor detail that really doesn't have a lot to do with what the control plane is, or how you look at a control plane. So what we've tried to do is make some progress in the industry by describing what we feel the important performance parameters are for control plane. And we have a white paper about this. I'll go through them here. First is, of course, you have to be very sensitive to what's happening on your data plane. So very fast device and link sensing. Ours is less than 100 milliseconds, and the ONOS part of that is less than 10 milliseconds. The applications, as they ask for things from the network, they're intense. Okay? There's a lot of throughput for that. So you have to be able to handle hundreds of operations per second on that. We're at 150,000 operations per second. You have to be able to respond to those quickly. So the latency to respond to an application is 50 milliseconds. And the flow throughput, where an intent is setting up a connection perhaps, turns into multiple flows, you have to be able to handle millions of operations per second for that. And we can easily handle 3 million operations per second. So these are the first numbers from Blackbird. This was our first opportunity to provide some performance optimization. As Cardinal comes out in May, you're going to see another 25% improvement on these numbers. And this is a continuing road. We're going to be always focused on the performance of ONOS and making sure that we don't compromise on HA and scale. Now we're going to talk about applications and POCs. Okay, central offices, there's a lot of them. AT&T by itself has almost 5,000. They're interesting places. They've evolved over 40 to 50 years. They're like museums. You'll find equipment there that you haven't seen for a long time. But they're a huge source of CapEx and OpEx. And we've been working with our providers to help them achieve the data center economies in the central office. And so helping them architect with commodity hardware, manage the fabric and infrastructure with ONOS, and be able to provide NFV orchestration. A second use case is the multi-layer SDN control. And as you know, the optical network, the IP network, maybe you have overlay of tunnels, those are all managed separately, possibly by different silos. They're over-provisioned to be able to handle any faults that come up. They're not very dynamic. And what this use case does is it shows you by using ONOS and controlling each of the layers in a coordinated way how you can really wring out a lot of the inefficiencies there and get very high utilizations in all of the different layers. An interesting transport or MPLS migration strategy is one that's called cap, grow, drain. And the idea here is that you're trying to get to a dynamic optical network where the majority of your flows are. And so what you do is you start capping what you put on your MPLS network. Maybe you take your elephant flows and move them to optical. And over time, you move more flows to optical. And eventually, you've drained all your traffic off the MPLS network. You've got a dynamic optical network. And so this is a great way to bring SDN to a backbone without a forklift upgrade. Okay, seamless SDN-IP peering. How do you take and create an SDN island and interconnect it with your existing IP? Well, it's really pretty easy. There's an SDN-IP application with ONOS. It has a BGP speaker in it. So through that, you can peer with other autonomous systems. You can make your SDN cloud appear like an autonomous system, and the routes that are learned are easily transformed into flows in the switches. It's an application that lets you talk from the SDN network to your IP networks. It lets you use the SDN network as a transit network. Even better, it's really highly available. You can lose an ONOS instance. You can lose an SDN-IP instance. You can lose connectivity to your external BGP, and this will all keep running. And this is in production in a network in North America called Internet 2, as well as one in South America. So these are our deployments. We start small with our own office. That's where we eat our own dog food. And it's a great test case for us for reactive forwarding. The next one was mentioned yesterday in collaboration with ESNet, RNet, Google, and Corsa. We had set up to show that using ONOS, it can have BGP peering with not only standard routers, but also with another router that Google built using open source pieces. So two different open source routers, one based on ONOS, all peering with regular routing and exchanging 15,000 routes. And yeah, 15,000 not huge, right? But we just started with this. So we'll be at hundreds of thousands of routes soon, and this will continue to evolve. We have an intercontinental deployment, starting with Internet 2, controlling 30 switches in the core on their AL2S network. That's connected with AmLite in South America. We're in the process of connecting with JAONT. And currently we have 12 universities and research institutes exchanging routes. And that's providing them with L3 communication without having to have core routers. So ONOS is starting to have a global footprint in the R&E networks. Here's a picture of our ecosystem. ON.Lab, we're the ON.Lab, I hate to say dictator, so I like to say shepherd. We're the benevolent shepherd for ONOS. We have a great group of partners in service providers as well as vendors. And we have a rapidly growing base of collaborators, people who bring great value to the ecosystem. And then we have a growing community of individuals as well. Some of the service provider traction that we're getting, and these are either POCs that are in progress or the POCs under discussion, or they're different levels of interest, but there's some themes here of the central office being re-architected. There's the packet optical and multi-layer. There's transport SDN. There's mobile cloud. And then DirecTV has a really interesting one that they're working on with multicast content distribution. So a lot of great traction in service providers. Okay, so in closing, I'd like to say that ONOS is really the only network operating system that's been purpose-built for large operating networks from the beginning. We've had an attitude of no compromise on performance, HA, and scale. We have powerful application and device abstractions. We're gaining a lot of momentum, as you can see from performance, the POCs, and the community growth. I encourage you to evaluate it, compare it, and come join us in the mission to transform operator networks. So thank you very much. Appreciate your time.
You just sort of glossed over what AT&T is doing with Cord. Can you explain that?
Sure. So Cord in the central office, if you can first build a fabric, which gives you nice east-west traffic capabilities, and the pieces today that are hardware in the central office, things like the optical line termination, you can pull the CPE devices and virtualize them and bring those into the central office. So virtual CPE, virtual OLT, fabric controlled by SDN, and then the capability to run NFV there, right? And so we're going to show at ONS how a subscriber can come in, set up their profile. They'll get a certain type of service. They'll go to the portal. They'll add some services. You'll get to see what's been added. Just how a user can provision their own services and how that's all virtualized right in the central office. So thanks for the question, Dan.
Yeah, hi. I noticed one comment you made about no core router needed. I think maybe that was your international deployment, maybe. And yeah, when I think of this, I think of high-performance core routers, Juniper, et cetera. Very high cost, a lot of silicon. I mean, do you see this as the evolution to replacing that type of solution with open, low-cost hardware? I mean, you mentioned Google, Microsoft. Is that really the direction that we think we can go?
Absolutely.
I mean, it's exciting to see the architecture. You know, it's almost hard to believe that we can do that.
Yeah, having been one of the people responsible for the CRS in Cisco, I guess I feel like I'm trying to kill my own child, but but yeah, absolutely. I mean, I don't see any reason why we can't get there. I don't know. It's anybody's guess what the timing is. And I wouldn't underestimate Cisco and Juniper's capabilities either. You know, Eric will just lay back and let it. You know. So I think there's a lot of interesting twists and turns along the way to getting there. But certainly, from a technical perspective, sure, you can get there.
Okay, thank you very much, Bill. I think if there are any questions.